In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the shadows. The Einsteinian demons. These creatures thrived in the distortion of space-time, causing chaos and disruption. The world needed a hero, and Miller was ready to answer the call. With his flute in hand, Miller played a tune that echoed through the cosmos. Each note, a shot of pure ether, struck the Einsteinian demons, dispelling them back into the void. The world was saved, not by a warrior, but by a...
All right, hello and welcome everyone to Ether Cosmology, roundtable number 85. Today I'm going to be getting into flat Earth and the globe Earth models, the 24-hour sun, and where is your model? This presentation is dedicated to my good friend, Jaron Campanella, who a lot of people are upset with because he went to a location on Earth, saw something that is said to be only exclusive to a globe, and therefore only the globe can predict it. And he changed his opinion about the shape of where he lives, and a bunch of people are upset with him. I was also on board with arguing the same model and using the same rhetoric with how he was arguing it, and I didn't change sides, and I don't feel like I'm any more of a shill or liar than he is, because he actually followed through with it. The reason that I didn't is because I went through a series of evidences and found that this model it doesn't predict things in the way that you might think it does, right? It doesn't. We're given this nice construct, these maps, and we're told that they function a certain way based on certain parameters. So now we're going to get into how these maps were derived, how to use them, how to use this model, right? We're given this model, right? But we're arguing over conceptions here. So I'm going to get into the full history of the globular model and the dangers of arguing with through rhetoric, without using anything, without manipulating independent variables or anything like that. Just observation alone can't tell you the nature of this place. We'll go ahead and get into the Prezi now. All right, so to start us off, from 1543, we have Nicholas Copernicus, who put forward the model that we're all enjoying now astronomically, cosmologically. So let's take a look at the full context of what he is saying here on the revolution of the heavenly spheres. So back when he proposed his idea that the Earth was in motion, to use his conceptualization to explain things, the church got mad at him because, the conception before was that the Earth was stationary, immovable, all these things. So he was directly going against what they were putting forward. So in the context of that, he writes a reply, and this is what he says in it. In regards to the hypothesis on whether or not the Earth is stationary and there are circles around us, or we do ellipses. But since for the same movement, varying hypotheses are proposed from time to time as eccentricity or epicycles, so circles or ellipses for the orbits. For the movement of the sun, the astronomer much prefers to take one which is easiest to grasp. Many philosophers demand probability instead, but neither of them will grasp anything certain or hand it on unless it has been divinely revealed to them. So we can speculate and do things and calculate all we want, but we don't know anything for certain unless it's been divinely revealed to us, right? Therefore, let us permit these new hypotheses to make public appearance among the old ones, which are themselves no more probable, especially since they are wonderful and easy to bring them to the vast storehouse of learned observations. And as far as the hypothesis goes on whether or not it's the Earth moving or the bodies moving around us, Let no one expect anything in the way of certainty from astronomy, since astronomy can offer us nothing certain, lest if anyone take as true that which was constructed for another use, he go away from this discipline a bigger fool than when he came into it. Farewell. So, what does that mean exactly? Well, what he's saying is they don't care about why the bodies in the sky move. They only care about can they predict where they're going to be tomorrow, where they're going to be a year from now, etc. The math to describe these doesn't involve dynamics. It doesn't involve cause. You could say anything, right? All they care about is changing positions. So we can have circular orbits represented by a geocentric Earth, everything moving around us. You could do a Neo-Tycho system. And shout out to the Tycho lads. They actually use the first order measurements of interferometry to say that the Earth's velocity is 10 kilometers a second rather than 0 or 30, right? Because there actually is no measurement that corresponds to the Kepler and Newtonian and Copernicus paradigm. If you were going to try and use the first order velocity measurements, this would be the one you would go for. So shout out to the lads for trying to make it happen. You could also hit up your boy Kepler and do some elliptical orbits for everything. Doesn't matter, all the same. Or if you take the Einstein preference and you feel like dabbling in some absolute differential calculus and you want to take some sections of a manifold and describe the curvature in space-time as a function of conservation of mass into and energy into a gravitational field, we can do the old curvilinear where the bodies are moving in a straight line, irrespective of any ellipses or circles, but the time and space around them is bent due to the mass of the bodies. So you can do any of these. These are all equally valid somehow. So to really take that in, when Copernicus says nothing is certain from astronomy, we don't care. We'll just do whatever is easiest to grasp. Circles are easy to grasp. Ellipses are easy to grasp. Absolute differential calculus, little harder to grasp, but still works. Well, why does it all work? Well, in kinematics, relative motion is always true. Future predictions of motion are based on velocity, not cause. So you're just looking at something where it is in that exact moment, how fast it's going, and you're going to try and predict where it's going to be in X amount of time from now based on that current velocity. So a good example of this would be you could take a system, you could do a kinematic analysis on a satellite rotating around the Earth, or doing an orbit around the Earth. That's good. Or you could switch reference frames there and say that the satellite is rotating, or the Earth is rotating around the stationary satellite. Sorry, and that would be equally as valid in kinematics because we don't care about the dynamics of the situation. We don't care about the fact that this satellite doesn't have enough mass to pull the Earth. Like that doesn't matter. Don't care. It's valid based on the positions and changes over time. That's all kinematics are. Then we get into dynamics, which is the future predictions of motion based on cause. Relative motion is not always true in dynamics, and that can be shown through various examples, but that's kind of the mathematical aspect is kind of outside of the scope of this Prezi particularly. So we're going to get into some different ways on how we could differentiate between these two frames if we're just using observation. So a quick recap of where we're at with all this, right? We've been given this model of how we perceive the motion of the sky around us. And through that, a model has been proposed that gives us a velocity. It gives us several different wobbles. We have different precession rates to explain what different celestial phenomenon are, quote unquote, out of their expected positions. We're supposed to have a daily rotation and an annual motion around the sun, the two velocity components. And we also are supposed to have curvature. So that is the curvature is supposed to be the cause of why celestial objects are no longer visible when they go out of view. So there's a lot of assertions here baked into just watching objects in the sky move. So now we're going to see how we can figure out if this model accurately represents the ground we're standing on, or if it's a conceptual model used for another purpose, and if we're going to end up a bigger fool than when we came into this. All right, so we're going to start with the precession of the equinox, some of the wobbles here, and in particular here we're coming to NASA to look at this simulation. On the left here, we have the Earth reference frame, which is stationary. This is going to show us what it would look like if we were, if we had the God's eye view looking down on the Earth and we could see the sky rotating around the Earth and what that precession would look like. if the Earth were stationary. And then we can also see it from two different perspectives, from the space God's eye view, where we'll see the sky will be stationary and the ball will rotate. So we'll see what this looks like. This is kinematics in work, lads. These two are equally valid. If you're standing on Earth and you're watching the sky, you could derive either of these two positions and you wouldn't be able to refute either one just based off of observation alone. There is no observation that you could make just by watching the apparent position of a celestial body that will tell you which one of these is true. To do that, you will have to introduce an additional factor. You will have to introduce terrestrial structures to intersect with celestial phenomenon to test the two, to see which is truly moving, to see if the Earth partakes in the celestial motion as well. That's where we get into archaeoastronomy. And this is a field of study where ancient structures all over the world, from every different culture you could possibly imagine, all have different structures or references that they're using that are on the ground that intersect with celestial phenomenon that they use to keep time. So here we have the Chinchillo 13 towers here that were built, and we'll let Brian Cox give us a walkthrough on how these temples works, but I'll give you a quick overview here. So suppose you're standing here where my mouse is, you're looking at these towers on the ground. From the ground here, there's 13 of them. Well, on the winter solstice, on the vernal equinox, the sun's going to rise here on this line. And then on the winter equinox, it's going to be rising here. And throughout the year, it's going to come through these different points. And based off of which point that it rises at, you know which month you're in. And you can figure out what day of the year it is within 3 days of accuracy. So here's kind of an overview of what this looks like. We have the December solstice, the sun zenith, max point, vernal equinox, sun zenith again, and the June solstice. Oh, sorry, I had the things backwards. Before we get to the Brian Cox explanation, though, we'll watch a quick video here of Canva's getting me, boys. All right, we'll watch a quick video here of an Aztec temple that was built. It has a snake head at the bottom statue, and then the way that this tower or a pyramid is constructed, these are going to cast shadows along this staircase here, and it's going to appear as if it's going to appear as if there's a serpent climbing the stairs. And this happens every year on the equinoxes. Ignore the annoying drums. All right, I can't deal with the drums. That's actually infuriating. So you can look it up on YouTube. We will watch the Brian Cox video now.
I wanted to see the snake go up the thing. Can you just put the sound off?
Yeah, I can do that.
It's like, dude, I've never seen this procession before. It looks really cool, and the sound just
it is cool, but those drums, I can't do it again. I watched this video 4 times. So we'll go ahead and play it through.
You can, all right. This is like one day?
Yep, same day.
Oh, see, now I get it. That's very cool.
It is very cool. Those drums are not. But yeah, so the significance of that is it was built like 5,000 years ago. If there's an equinox precession of 50 arc seconds a year, after 72 years, there would be 1 degree of precession. After like 400 or 500 years, you'd have a whole day. Like the equinox would be on a different day. It's on the same day every year, guys. The statue, like that statue thing. The shadow thing happens every year. It's never changed. So like the argument would have to be like, oh, they built this before in their time when it wouldn't even have had a purpose. And then now in our time, we're just reaping the benefit because we've processed into where it happens to align. It's ridiculous. There's structures all over the world that were built at different times that all still have the same intersections with the sky or with the sun. So this will be significant in explaining what's actually causing the precession, what's actually moving here. So we'll let Brian Cox, we'll listen to him real quick, even though he's probably worse than the drums. But we'll listen to him real quick.
Around 2,500 years ago, a civilization we know almost nothing about built this fortified temple in the desert. Its walls were once brilliant white and covered with painted figures. Today, all but the smallest fragments of the decorations are gone. The details of this culture and all traces of its language are lost. And yet, if you stand in the right place, you can still experience the true purpose of Chankio in just the same way as you could the day it was built. But to do that, you have to be here before the sun rises.
These towers form an ancient solar calendar. Now, at different times of year, the sunrise point is at a different place on the horizon. Actually, December 21st, which here in the southern hemisphere is the summer solstice, the longest day, and the sun rises just to the right of the rightmost tower. Then, as the year passes, the sun moves through the towers until on June 21st, which is the winter solstice, the shortest day, it rises just to the left of the leftmost tower, actually just in between that mountain you can see in the distance and the leftmost tower. So at any time of year, if you watch the sun rise, you can measure its position and you can tell within an accuracy of 2 or 3 days the date. Today's date is September the 15th, and so that means that the sun will rise between the 5th and the 6th towers.
Chankio still works as a calendar because the sun still rises in the same place today as it did when these stones were first laid down.
You don't. Oh man, it doesn't pause. It just plays the next video. That's so annoying.
Right?
Around
All right. You got to make the video smaller when in the slide when you want to manipulate it.
Oh man, that's infuriating. Okay.
Yep.
So anyway, sun, same spot forever, but precession, right? So what do they say? The leap year fixes it or whatever. Well, what's the leap year? Well, every, what was it, 4 years or so, the stars shift back in their original positions. They go back to where they were. They drift a little bit throughout the year, all at different rates, and then they move back. So that doesn't, what this shows is that the Earth is stationary and the sun and the stars are moving, and their motion is independent of each other, and the stars are precessing. The sun is in the same spot doing the same thing. It's the stars that are in a different location. Now, we have discerned this based off of using terrestrial structures intersecting with the same point of the sun. If the Earth was the one that was wobbling in between the sun and the stars, none of these would line up. The sun, the equinox would be on different days by now. There would be an actual drift. There is, my boy just said it's been the same since it was created. So here's another example of this. This one's in India. I can't pronounce the name of this tower, but if anyone happens to know it off the top of the dome, I'm not going to stop you from shouting it out. But on the equinox, what happens? The sun sets through this building right here, and we see it pass through each one of these windows every year since this thing was built. So we'll skip through here. Oh God. Ooh. All right.
Wow, that makes me miss the drums.
Right? That was even worse. Oh, cool. Reset. Hell yeah. All right. Next slide. So the next slide is a Chinese observatory here. So this one measures the shadow that's cast from up here down here on this, the length of this. So at different parts of the year on the equinoxes and solstices, shadow length will correspond to a certain distance along this. So the purpose of this is to measure, basically the same way that they were using the 13 mounds for their calendar. They're using the shadow lengths on different days, versus specific checkpoints for the minimum and maximum lengths of the shadow
Yeah.
for where the sun's going to be.
This looks like elevation at noon kind of thing.
Yes. Yep. And this dude built, well, the guy that was in charge of this for the Chinese at the time was commissioned by, whoever, the emperor, to build like 40 of these all around China. So there's like 40 of these observation points, all doing the same thing, all different, locations, doing the same thing. Here we have a natural mountain peak that lines up with the equinoxes this is in Chocola. And we have the entire, like you can see the pictures here, where the sun is, and then when it isn't, where it lines up. The whole mountain ridge here is identical to what these lads made back in the day. That's pretty cool. Okay, so we have ruled out Earth wobbling as a possibility. Now, what about Earth's velocity that's asserted? There is one measurement of Earth's velocity, and that is through what's called stellar aberration. That is throughout the year, there is a drift in the stars, essentially. You can think of it that way, where they're not where they're supposed to be, by a tune that adds up to 20 arc seconds over the course of a year. When you ratio that over the speed of light, when you take the arctan of that using the speed of light and the velocity of Earth, you get the amount that was measured. You get 20 arc seconds. And so they were like, okay, that must mean that the Earth is moving around the sun at 20 arc seconds. At 30 kilometers a second to create this angle of deviation when we take our telescope and look up and do a zenith measurement. Because the star should be in the exact center of our telescope, but it's always a little off. And now we're trying to figure out why it's coming in aberrated. And this ratio here looks mighty fine because it corresponds to our Kepler, it corresponds to our elliptical model that we like. So there's a couple of things to follow up on regarding the speed of light and how to tell whether or not the Earth is in motion. So there was a measurement of light through moving water, where the speed of water affects the velocity of light. When a light beam was split and recombined at the other end of a tube that had running water going through it, the light was retarded and velocity boosted, depending on whether or not it was going with or against the flow of water. And there was a 88% proportional ratio of the velocity translated to the water, 44% boosting it with the water going with the light going with the water, and 44% retarded as the light went against the water. Which gave a fringe pattern over here when it was recombined. They take the square of the distance between the fringe, and they figure out that that the moving water here, right, is the exact, that's the difference in between what the fringes would be if there was no velocity between these and it just recombined with light going at the same speed in both directions. They were able to discern that they could measure velocity addition when they add a medium to it. So that's step one to here. So this is what you would call a longitudinal effect. The light is moving parallel with the flow of the water. So it gets dragged or it becomes retarded. So it just slows down or it gets faster. But there's also a transverse effect, which will be extremely significant when we get into the testing of aberration and whether or not it proves definitively that the Earth is in motion. So the longitudinal effect here with this diagram, pretty straightforward. The light goes through the running water, right? Light's going with the velocity of the water. It gets velocity addition. And we have the transverse effect where the light gets displaced. So what they were proposing, for an experiment coming up, is that if they added water to the telescope, that the angle would increase, that aberration angle would increase. And we'll get to the significance of that as we continue, because the transverse drag measurement had not yet been measured, only the longitudinal effect. And this is important because let's suppose you have like an interferometer, right? And it's, it would be parallel to the direction of motion. So you would be doing like a longitudinal test. It wouldn't be the same as the light coming in, perpendicular to the direction of motion, right? So that's the big difference here. But in 1971, it was shown through a rotating disc of plastic that light coming in perpendicular to the direction of motion always gets velocity addition in the displacement. Like it always displaces it. Doesn't matter. So like in the longitudinal, right, you can go with or against it and it'll like retard or whatever. But in this, it's always positive and it always displaces, irrespective of whether or not it's going with or against this rotation. So, and that was in 1972. So these ones are more modern, but we'll get to the some classic ones that also have a similar implication. So we have Arago Francois in 1953, who took a crystal prism and half covered his telescope to see if the starlight that gets intersected at the midpoint would change when it hits the medium. If the Earth is in motion, then this, the transverse effect there is going to cause an angle change the same way, that was measured here. Same exact premise. So this angle isn't going to be straight anymore. It's going to deviate. So, and we could figure out how much it's going to deviate based off of the refractive index and the velocity of Earth, or whatever assumed velocity is in question. That'll give you the output for the angle. So they predicted. So anyway, the conclusion to his experiment was that there was no change, and that the refractive index of a moving prism is the same as a fixed prism, which sounds preposterous, right? How can that be? Especially in the face of experimental measurement done in 1862. So Francois was done in 53. So perhaps maybe they didn't have this knowledge of the transverse effect and how that would actually work, right? But then insert Foucault here, who has a light source, a rotating mirror, another mirror for the light to reflect back off of, and complete a circuit essentially where he can take measurements. And then in between the reflection, the rotating mirror and the reflecting back mirror, he introduced a tube of water. So when the mirror is stationary and you shine the light source on it, it hits the mirror, hits the other mirror, reflects back, and you could predict the angle change based off of the orientation. Now, when he introduces rotation, right, before he puts the water in, right, before we get to the water, right, just in air, rotates the mirror, produces a deviation. There's an aberration angle, and it's a function of the velocity of the rotation and the distance traveled by the light. Then he adds water in it, and the angle got bigger because there was more rotation in between the time it took for the light to traverse the tube and come back in air versus water. So there was a bigger discrepancy. So the angle got bigger. So now, 1962, they have direct experimental evidence that shows that transverse motion through a medium will cause an increase in the angle change. Right? Irrespective of what you feel like, none of these in this hypothesis, none of this was about ether or anything. This was about two different models of light, one propagating through waves, one propagating as a ballistic projectile. The ballistic projectile theory predicted that in the water, as a function of the, or like as the inverse of the density, it would accelerate based on how they were doing their math. Well, that wasn't what was measured. So they falsified that theory. They showed it was less likely to be true. And the wave theory, which made the correct prediction for how the light or how light would behave in water, and also how it would behave with the moving medium or the rotating reflection mirror, etc., made the correct prediction. So they were like, okay, we know what's up. So a little bit before Airy in 1871, a guy named Klinkerfuse did a similar setup where he took a zenith mount telescope, filled it with a turpentine, looked up and said that he measured an angle increase. So astronomer Royal George Bedell Airy was like, oh, okay, well, I need to verify this because that's awesome. That'd be a great thing if we could show that. And keep in mind, Klinkerfuse's hypothesis was about if the motion's real, right? It's a dynamic thing. It's not apparent. It's not fake. If there's real motion and we introduce water here or turpentine, then this angle has to increase just based off of this. This is basic math for what they were using to derive. This is what has to happen, independent of any ether theories. And he even went on to say, regarding Fizeau drag, that it's possible that that has a part to play in it, but because there wasn't a transverse ether drag test at the time, he was like, we can discount that for now and only look at this in terms of like, is motion a real effect? This is how we can find out. So when Klinkerfuse says that his or I'm sorry, when Airy says that Klinker-Fuse's hypothesis is untenable, it was because when he added water to the telescope, the angle didn't increase. And the implication of that is that the starlight already comes in with a velocity component to it, a horizontal velocity component. It's already coming in at that angle with respect to a stationary Earth. If the Earth was the thing moving, like in this experiment, then the angle would have increased. But it stayed the same. So the implication is that we are stationary, starlight comes in. Now, Airy says that the aberration measured is in air is the same as measured in water. Does that mean that he concluded that the Earth is in motion still? That's not what that means. That's just a reporting of what happened, guys. He's not asserting anything or drawing any conclusions in his paper. He's just saying, I put the water in, the aberration angle is the same. Klinker-Fuse's hypothesis is untenable. His hypothesis was that he could make a first order measurement of the velocity of Earth through space using water to slow down the light, which would cause the Earth to have an increased distance traveled, which would create a bigger angle. Wasn't measured. And on top of that, another thing to note is that this all started back in 1725, something like that, with James Bradley measuring aberration from Gamma Draconis. And then Airy did the same thing about 100 years later, 125 years later, something like that. Then we have, to this day, right, those same stars, same exact spot every year. So if there's any precessions or wobulations or anything like that, right, those you couldn't keep doing this and repeat it. Yet they do. And the star will be there again next year. All right. So there was a final, more definitive test where they separated the wavelengths of light doing interferometry and using the square of the distance between the fringes. They determined that the velocity measured was 6 to 8 kilometers a second instead of the predicted 30 kilometers a second to substantiate Kepler's laws and Newtonian dynamics. Right, because you can derive Newton from Kepler and vice versa, but Kepler is just a ratio of periodicity in pi, and Newtonian dynamics is gmm over r squared, which is supposed to be the gravitational potential constant and the mass of the two bodies to assert the dynamies. And then we got the radius, which gives us our pi, but the mass cancels out, the constant doesn't do anything, and it just becomes a ratio of pi and periodicity again. But the reason you can derive the one from the other is specifically because the asserted dynamic cause algebraically cancels out, meaning it couldn't possibly be the reason for the motion. All right. That's extremely significant because all that exists is a math ratio. It doesn't have to have physical meaning. It could represent a periodicity, certainly, but it doesn't mean that there's any physical dimensions associated with the ratio. And that's extremely important because when they calculate things like the orbital diameter and using astronomical unit and all this stuff, these are all things based off of ratios that don't have to have physical meanings to make the correct prediction. It's just based off of periodicity when you'll see it next. And that corresponds to how fast it would have to be moving. And you could adjust that based off of, and to compensate for that, you would have to adjust the distance as well. So it scales inherently as a function of the periodicity. It doesn't mean that that's a physical distance or anything like that. Right? It's a conceptual model, as the boys have asserted. And then so when Michelson came around measuring the wavelength of light, showing that, which is way more accurate than just the angle measurement alone, because we're getting into the wavelengths now, which is way more precise. And we can see that the velocity isn't corresponding to these dynamics that are asserted, right? So 1887, after all this time that's transpired from our boy Copernicus, we're still no closer to having a conceptual model of the cosmos that actually explains anything in terms of what this planet is, and why it's moving, or what this celestial body is and why it's moving, right? we only know why it's moving. That's all we've ever seen is why, or it moving. We don't have no idea why. So that was the recap there that I kind of went over. Whatever this place is, we have ruled out terrestrial motion as the cause of celestial phenomenon. Using ancient structures, we have determined that the relative motion between the sun and stars has nothing to do with our motion. It's between the bodies in the sky themselves, not us, or with respect to us, rather, being stationary. All right. We went over all of that. All right. So next up, we have Earth curvature, right? Because there's a explanation given as to why we can't see celestial bodies anymore. So that'll get into, although I wouldn't traditionally consider that a dynamic prediction, I feel like we could definitely make an argument for it to be one. So this is an asserted dynamic cause as to why the bodies are no longer visible. And it starts back with a little story from a gentleman in Syene in Alexandria, and the 428 nautical mile distance between them that definitely wasn't already measured, and they had values for that were accurate because they were all using the same coordinate system. But anyway, using the angle deviation on the sun as it passes through at its zenith point at the equator, we have this deviation angle of 7.2 degrees. And that 7.2 degrees is 1/50th of a circle. You can divide that by 360. And so you multiply the 50th of the circle by the distance between the two wells, you get 21,400. And that's within 1% of the accepted value of Earth's circumference given in the nautical miles that we use today. So what the big claim that's talked about for this in terms of flat Earth versus globe is typically the assumption made on the distance to the sun and how it doesn't matter. But the real showstopper is that they're asserting that a stadia, which there's no official definition of a length of a stadia, right? It just depends on what academic source you're citing and how much they wanted to make it agree with current values to make it seem plausible that whatever historical narrative they're asserting is definitely correct, because at least it has the dimensions of the Earth in it, and those are correct. So you can definitely rely on the correctness of the rest of it, right? So the accuracy from a stadia compared to the current nautical mile can be anywhere from 0.1% to 16% accurate. And I think that's
the factor of 1/50th is just the geometric accident. It says right there at the bottom.
Just an accident, dude. An accident. So we're going to continue to see if there's any validity to this curvature. Right, so we're going to look at celestial navigation specifically, which uses the positions of the celestial bodies to navigate all over the world. And we're told, from the baseline of this story, that this corresponds to a distance length that corresponds to distances that are derived using the current latitude and longitude system, which is what we use for celestial navigation. So there's still like the connection here that they're trying to instill in us is that, how could he be right using this completely independent unit of measurement? And then we're also using a completely independent unit of measurement and we got the same value. Oh, that's so crazy, right? But the only way that you could get this is if the stadia was also a ratio of a terrestrial meridian, which is what a nautical mile is. That's why these values give close approximation. So it was how much of a terrestrial meridian do the scholars want to say a stadia was? And given that ratio, that determines whether it's 0.1% or 16. Anywhere in between there, right? It has no physical meaning. So now we're going to learn about celestial navigation. So to start us off, we're going to use Henning's guidebook here. And this is was a fantastic read. I highly recommend this this PDF for everyone. It's a great read. So the basics of celestial navigation. Celestial navigation is a branch of applied astronomy. It is the art of science of finding one's geographic position through astronomical observation, particularly by measuring the altitudes of celestial bodies, sun, moon, planets, and stars. Okay. Sounds pretty straightforward. An observer watching the night sky without knowing anything about geography and astronomy might spontaneously get the impression of being on a plane located at the center of a huge hollow sphere with celestial bodies attached to its inner surface. All right, that sounds precarious. Indeed, this is a naive model of the universe that was used for millennia and developed to a high degree of perfection by ancient astronomers. Still today, it is a useful tool for celestial navigation, since the navigator, like the astronomer of old, measures the apparent positions of the bodies in the sky, but not their absolute positions in space. This is extremely important because every conceptual model that's been put forward thus far, especially ones that try to attempt to not only explain why there's motion, right? Because in the sky. So like some cultures would say, there's a big bird up there flapping its wings and that's causing the bodies to move, or there's a dragon in the sky breathing, whatever, right? There's different explanations. What was it? Kepler thought that the sun was singing a heavenly song and the acoustic vibrations of that was causing pressure differentials within the celestial bodies that would make them move. So like all we have is the motion, right? We don't know why yet. Let's see. So in particular, right, using the apparent position of the bodies, that's extremely significant because when you look up at the sky and somebody else looks up at the sky, you two might be thinking that you're looking at the exact same object, but that object is independent of the other person. It is specific to you. Everything you see in the sky is projected into your own hemisphere of vision. That's how you perceive it. That's how you perceive sun rays. That's how you perceive rays on a beach, etc. That's why sun rays don't go to the ones that go to you aren't going to your friends. That's why you don't see a big giant. That's why the entire beach isn't just one big sun ray, right? It's individual and personal to you. And that's extremely important because if we're all seeing a close approximation of where these things are, but not quite the apparent, but not quite the true position, then we can't really say anything for certain about what's going on with the motion up there. So we already touched on earlier about how a nautical mile relates to distance on the ground, but now we'll get into a recap of that. So continuing on with our Umland guide, 1 nautical mile is equal to 1.85 kilometers. This is a great circle distance of 1 minute of arc. So if you took a 1 minute of arc going around the equator, that 1 minute would be 1 nautical mile, which would correspond to 1.852 kilometers. And then everything metric system or imperial is derived as it's a ratio of this, of the meter, right? A meter is 1/10 millionth of a terrestrial meridian. So if you were to use this coordinate system that's supposed to represent positions of the bodies of the stars and units of measurements that are derived from said coordinate system as a length, you could do trigonometry to calculate a distance based off of an elevation angle to a celestial body, traverse that distance, and then look up and see if that star that you calculated is in the center of your telescope, which is extremely important. And we'll kind of come back to that in a little bit, but that was how they related sky miles to ground miles. So chapter 3 covers geographic position and time. A circle on the Earth's surface is one who passes through the center called the Great Circle. So the biggest part of that would be the equator. So the equator represents the Great Circle on the surface of the Earth. Then any circle that is smaller than that is a small circle. So the equator is the only one whose plane is perpendicular to the axis of rotation. And then the meridian lines, the longitude lines are intersect as well. but vertically. All right, then we've got units of measurement. We've got observations of terrestrial bodies, right? We're measuring elevation angles to apparent positions of bodies. All right, checks out so far. Let's swing back to 1777 real quick and see if we can see what they were talking about, how to describe this as a model here. Like what do we do with this, right? So in section 2 here, in the doctrine of the spheres, they give reference to how you see in one hemisphere at a time. There's 2 hemispheres that you can see in based off of what side of the equator you're on, and how you perceive everything is your regular horizon that you see from the ground to the sky, and then the sky is the hemisphere projected into your dome of vision. So this is all laid out in 1777 on this book called Grammar, wherein the situation and extent of the several countries are laid down according to the motif exact geographic observation in the history of the different kingdoms of the world, and interpreted in such a manner as to render the study of useful. Basically, this book is they're saying they're going around to all different cultures and asking them like, hey, what do you believe? How did you, and why? And so when they were covering the jolly old England lads, they were talking about what they were teaching for navigation and how they taught it and what it is. So this is all the same thing that we've been talking about for quite a while now, dating back to 1777. And then here we have, what was this called, Shane, over here on the right?
Armillary sphere, I think.
An armillary sphere. And what does the armillary sphere do again?
It represents the celestial heavens as static, geocentric, observer-centric positions, right? A perfect, all smaller circles, really.
Awesome. A series of outward concentric circles representing motion around a fixed point, huh?
It had to be built for your location, specifically enough, right?
Oh, interesting. I didn't know that it was like that. So it's not just like a conceptual model. It was actually relative to your location.
Well, it's angled for your latitude, that's for sure.
Yep. Latitude dependent. Yep.
Oh, I see. Yeah, because okay. Oh, dude, I thought it was just a toy. That's so cool. That's much better. That's awesome.
Oh, it's like an upgraded astrolabe. I don't know if you call it upgraded, but
Yeah,
It's
no,
like a sundial on steroids.
Yep, no, I get it now. That is insane. So these degrees are actually
around the
where
equator?
yes, that is awesome.
Yeah, it actually says horizon in the foreground of the equator there, and it
Ooh.
shows you the hours of the day going from off to the left there, right?
yeah, it's like a
Just like
movable
sundial has
crate.
those on the horizontal.
Yep. That is awesome.
There you go.
A movable Prague clock almost, right? Prague clock, whatever.
Prego? The Prego clock?
Yeah, that's Prague. Yeah,
it's like
that's Prague.
Stone's not here. He's not going to correct me as I was thinking.
All right, so we'll head back to 1892 real quick and see what the old and new astronomers are saying. Overhead is the dome of the heavens, which has been determined by the actual position of the visible bodies. So the apparent position of the bodies, great. Like heavenly orbs or the blue sky or the clouds have in reality, no definable shape, but which may be geometrically regarded as a hemisphere around the center here, denoted by O at the center. And this is indeed the natural idea of the observer, who the dome of the heavens appears to be somewhat flattened at the horizon, or flattened form, the horizon being between 3 and 4 times away the region overhead. Oh, no way. So you see the night sky of the hemisphere projected into your dome. Nice. All right, and considering the cloudy sky, we have to remember what we rightly understand. What we see is that there is usually a curved surface that which looks flatter than it is. We mistakenly attribute this dome shape to the heavens, whereas in reality, the curvature is no greater than the curvature of the Earth itself, which under ordinary conditions is imperceptible. What kind of conditions would it take to see Earth curvature, do you guys think? Do any such conditions exist? Anyway, so big takeaway here. They're teaching the exact same thing, right? 100 years later, roughly. Same exact scenario. So now we're going to take a look at the first point of Aries and what that means in terms of finding your geographic location using celestial navigation, using this coordinate system, using the latitude and longitude system that is bound by the position of the stars. So when you see a latitude and longitude on a map, on an AE map, on a globe, if you hear somebody say latitude or they say longitude, know that they're also talking about a snapshot of the sky on the vernal equinox, which is called the first point of Aries. So here we have a equirectangular projection of the bodies or of the constellations in the sky at that time. And then we have what that would look like projected out on the same thing, but just, what it would look like on a disk. Same exact scenario, represents the same thing. But the most important part is that it is a snapshot of the sky. It does not yet correspond to ground positions. So when we look at old maps, when they would have the two star charts, and they have a northern hemi and the southern hemi. In the northern hemi, you use this side. You're in the southern hemi, you use this side for your reference for where the stars ought to be on that first point of Aries on that night. That's extremely important because as we continue, we're going to reference this snapshot so we can determine our Lati and Longi, or more importantly, our Longi. The Lati is much easier. So so again, this is just relating the nautical mile to things on the ground. So we have sky miles, things going on in the sky, rotation at 15 degrees per hour, moves at 15 arc minutes, corresponds to 4 real minutes. 1 arc minute corresponds to 15 real seconds. 15 arc seconds corresponds to 1 second. And distances over these fractions of the of degrees here, we have 69 miles per degree. So 1 degree of this, 69 miles. 1 arc minute. I'm sorry, 1.5 miles for arc minutes, and then in arc seconds, the sky would move in 101.2 feet. That's how you would relate these measurements to how fast the sky is moving relative to your ground position. So we went over the conceptualization of the celestial sphere, but we're going to break it down a little bit more so we can really grasp it in there. So the celestial sphere is made up of 3 coordinate systems of horizons: the sensible horizon, the visible horizon, the geoidal horizon, and the celestial horizon. So the geoidal, sensible, and visible are all basically the same thing, but the geoidal is a little lower than the visible. But because of refraction, they, you only see the visible, blah, 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 right? Whatever the curve is, it's refracted up, so you don't actually see the curve. You just see the sensible horizon. Now, the next important part of this is that the celestial horizon also makes up the other component. So this horizon part is from ground to sky, right? The geoid to the visible is the ground to sky. From sky to ground, you have this that is incorporated by the celestial horizon, and the celestial horizon is from intersects with the equator. Okay, so what they're saying here is you have what you see on the ground to sky, and then you see from sky to the equator in the sky, as the lad mentioned over here, right? You see, or what was it? I think it was that guy. He was saying that you see like 3 to 4 times the distance or whatever of the sky. So like that's what that relates to. That's what that's supposed to mean. And we know that this is true because what they're going to end up doing is transform this observer to where he is and put him at the center here to use this as we continue. But again, this is if you were an observer standing on Earth and you were observing the heavens around you, you would assume a flat plane. You would assume that the sky, which is your celestial horizon, and the geoidal / visible horizon are coplanar with each other all the way out to the equator. That's what you're assuming with this. And within that, you are taking elevation angles to the bodies. And as those bodies are further or closer away from you, that's going to dictate, their elevation angles, higher or lower. Excuse me. Okay. Now we have the terrestrial sphere, right? So this is going to be how we're going to relate the positions of the bodies to the ground. We're going to use the Greenwich hourly angle and declination, which is just going to be the same as the azimuth and the elevation angle. These are all the same things. Let's see here. So the difference here would be, instead of being an observer on the top of a ball, right? This is going to put us at the center of the ball. So we need to move this lad from the top of the ball to be in the center of the ball to merge these two so we could use them. Now, there's a couple of additional steps, but before we can start applying corrections and figuring out the adjustments, we need to move from the top of the ball to the bottom of the ball. So here we have the merger of the two systems. This is what this looks like. They are exactly the same now. We can now that we've moved to the center of the ball, we can then go over the series of corrections necessary to partake in celestial navigation, to use the positions of the stars to relate them to positions on the ground based on time. And when we do that, we create circles of equal altitude around us that intersect. And at the intersection points, we can determine our location. For most instances, you'll be able to reference two stars. In the intersection point, you'll know, okay, I'm over here, or I'm not over here, right? Because the distance between them is pretty great. So like if you left in the northern hemisphere, the chances that you're suddenly in the south, right? So you can deduce from that. But if you need to, you could do a third one, and that will give you, well, you can only be here. It's not intersected with the point down here. It's a third one, right? So if you had to, you could do 3, and you could double extra know if there was any ambiguity. So the big claim here is that anyone standing along this circle will see the star at the same elevation angle. And this is due to incoming parallel light rays, et cetera, et cetera. Or is it? Well, we'll continue on and see what happens now that we understand what the purpose is of what we're doing here with these circles, or with these elevation angles, what we're going to do with them. Okay, now it's said that the elevation angles only work on a globe, right? So if you were on a globe around this circle of equal altitude, you would have these corresponding elevation angles. If you were to try to do it on an AE, I'm using air quotes, on a flat Earth map, you wouldn't be able to do it because of the distortion here. Well, your circle would also be distorted. You would have to apply the proper corresponding correction. Shout out to Shane, the map projection correction expert, who shows us what the circles of equal altitude look like on the corresponding projection. It's not an issue at all. It doesn't matter. These are the same. In fact, this latitude and longitude system represents the exact same thing as the globe. What most people don't know is that there's a little tiny globe projection hiding behind the AE projection. They're the exact same. One is not a flat Earth map, and one is not a globe map.
That's hilarious.
They're all projections
out back there
of the same thing, right?
Get him.
And we'll show, and this gets into arguing conceptual models and using rhetoric rather than measurements that include manipulation of independent variables and things like that, where you have intersection points with terrestrial and the celestial to make the determination on is this body behaving in a way that corresponds to the ground beneath me being curved? Because we can definitely test for that, but just by looking at it, we can't know for sure. So here again is just a different location, same thing. And you could see when you're closer to the north, the correction that's applied, like how it changes basically, because as you get further out, they're more expanded. These are the same thing, right? Never forget that the quote unquote globe projection is always right there behind it. They are equivalent. All right. The big disclaimer about arguing conceptual models and arguing things that describe the apparent position of celestial bodies. And this was a big part of rhetoric in being able to articulate and argue for flat Earth, because the argument was that the sun is in between the tropics creating a circle, and that there would be no scenario where the sun there would be a 24-hour sun in Antarctica. Now, some people say that they weren't even sure that there was an ant-arcing motion of the sun in the south, and but I don't know about all that. But based off of just the arc and antarc there, right? We were saying that there still wouldn't be a 24-hour sun in Antarctica on a flat Earth map using this conceptualized model, right? If you were to conceptualize this as like a physical body, this is where the sun is. This is where it has to be, then you are locked into that 100%. I'm not going to sit here and say that you're not. Now, the thing is is that because of the all representing the same thing, it's like, what does this actually what is an AE map anyway? Like, what does it represent? Well, it's got the latitudes and longitudes on it. So we know it represents the position of the stars on a specific night. But what else does it have? Well, the AE map in particular tells us the position of the starlight distribution throughout the year. So in referencing that, it's literally the exact same thing. So like the two models, the Walter Bislin / Shane model / the, I don't know this gentleman's name, but whoever made this model, they're all representing the exact same thing, where the apparent position of the sun is going to be. Now, if the sun circles around us, like in reality, but we perceive it arc or antarc based off of our hemisphere, right? We need to then say, okay, is this due to curvature, or is this due to some other thing that isn't affected by ground curvature? How are we going to be able to distinguish between the two? Well, as we continue on, we'll learn about some different methods using intersection points with the terrestrial and the celestial. But as we continue here, let's just take these as conceptual models here, right? And we're learning how to use said conceptual model to see if it even corresponds to anything in reality. Okay. So I mentioned the first point of Aries, right? That snapshot of the sky for the longitudes and the latitudes. But we also have our sidereal hourly angle. Okay. And what that is when we look at the stars, right? We see it in an apparent position, but we need to move it a little bit. Well, how do we move it? Well, we take the reference point of the first cusp, or the first point of Aries, and we add that to our sidereal hourly angle, and we also add the difference from the Greenwich meridian, right? So we add up the difference between all of these, and then now we know where our star is supposed to correspond to a ground position now. Or, well, we're getting closer. There's still a couple more steps. There's about 5 or 6, depending on what bodies you're using. But we're getting close now. So we've got our reference points. We've got the Greenwich meridian. We've got the first cusp of Aries, and we've got our apparent position. Now we're adding these up, figure out where the star is supposed to be to correspond to a ground position at a specific time. That was dictated to us. Shoot, one second. That was dictated to us. Oh, and okay, so let's back up a second. So the usefulness of this coordinate system, right? Because maybe you don't want to do this. Maybe there's a different way. Maybe we could do it differently. How'd they do it before, Shane? Didn't you say they started a campfire and measured Jupiter's eclipses? See how long they see how long it takes water to boil.
Like in the longitude equivalent, they would just get a time component, right? So they used Jupiter's moons, they used lunar transit methods. So like the time it would take the moon to pass via a certain area of space, all different metrics of trying to approximate that 15 degrees per hour, essentially. But yeah, it definitely can be done without it.
Nice. So once they've got a timing component narrowed down here, they can quote unquote change the position of the star to where it needs to be to use their coordinate system. And the coordinate system that was given to us, this nice latitude and longitude system, was given to us via the dictation of the king in 1776, where they say that anyone using a bootleg or unauthorized navigational tools, so almanacs, tables, anything like that, you were going to be fined $20. And that was huge back then. That would basically, it was $20 per item of contraband or whatever too. So that would basically financially cripple you if you were not using their licensed and approved methodology. And they also put out a bounty here. They were putting out a reward for the mathematician / astronomer that would go out on dual trips around Great Britain, one going clockwise, one going counterclockwise, using their latitude longitude system, and a method in which they could calculate longitude down to a half a degree. So if you can get it down to half a degree, they gave you 10,000. Third of a degree was 7,500, and then 5,000 for 1 degree. We're using this system for a circumnavigation trip around Great Britain, clockwise and counterclockwise. Now, in here, they mentioned that there's an unannounced standard that has to be met. So basically, whatever methods you put forward to make this to make use of this coordinate system useful at sea, it has to be backwards compatible with their unannounced standards here, that they'll tell you like when you're submitting it, right? They didn't make it public, but that is part of what they put forward here. And then after a year's period, if your stuff worked or whatever, and they all voted on it, you would get your money. And this would be like the equivalent of somebody handing you $2 million today because you fixed their car or something, right? Like in terms of the money relation. Okay. So we got coordinate system. We got it's now being imposed by the state, and we've hired people to make sure that it works. So now we're going to look at some nautical almanacs, and we're going to look at the references in there for celestial refraction in particular, because that is a big part of adjusting the apparent positions of the bodies to make them compatible with said coordinate system. Excuse me. Let's see here. So a big part of this is that there are two views here, right? So when we're making our observation here on this would be our topocenter view here, right? And then we would have the geocentric position, which is going to be at the center of the ball. So this book, in the Supplemental Nautical Almanac, that covers the history of how the corrections and improvements were made to the almanac, which is basically going around and taking zenith measurements of stars, which, and comparing them to where they're quote unquote supposed to be relative to this geocentric coordinate system, which when I say geocentric coordinate system, all that means in this context is you're at the center of the ball so instead of standing on it, you're 3959 in the ground, and you're looking directly up as if there's no atmosphere, and you're just taking a raw 90 degrees zenny from the center of the ball, not on the ball, right at the center. Let's see here. So they talk about the refraction corrections here. So I wanted to get some citations to look at for what the celestial refractions are, because that's outside of the scope of this book here. They're just talking about the coordinate system transformations between topocenter, geocenter, heliocentric, barycentric, and although they don't use the barycentric, but they include it just, because for funsies. But anyway, it's a relationship about that and the transformations and the corrections for the deviations based on the ellipsicity nature of Earth, right? That eccentric nature, the eccentricity or whatever. All right, so we got our list of citations here for refraction, the theoretical discussion and calculations of refraction. And what it turns out to be is it's mostly theoretical calculations, which we'll get into as we continue. But now that we have learned about how we view the heavens, what we're gonna do with the positions of the stars in the sky, now we're gonna look at the step-by-step calculations now. So we have an index error, and that's going to be subtracted or added to our measurement depending on the calibration of the instrument, on whether the error is positive or negative. We will remove that from our angle of observation, which will give us a slightly new angle depending on the severity of the correction, right? And if we are above if we're off the ground, right? If we're in an airplane or if we're on a boat, we're not quite on the ground, we hit up the dip correction. The dip correction, 1.76 times the square of the height of the observer in meters, or 0.97 if you're doing the square of the height in feet, is a coefficient that basically extends this ground, right? It extends the ball to your new location. Now, because you're not actually moving, right? But we're doing these theoretical transformations to the center of things and moving things up. What we're actually doing is readjusting the position of where the expected position of the star is supposed to be in the sky, even though we haven't done anything or moved yet. This is what we're setting up for. So we got our dip correction, and which already has atmospheric refraction and Earth curvature baked into it as a function of this coefficient here, which is the
So-
Go ahead.
Just to be clear, Alan, for the crowd, that's the dip angle in minutes, equaling 1.76 minutes times this particular factor,
Yes.
or 0.97 minutes, as in 60ths of a degree. Keep that in mind in terms of significant figure when we're talking about all the corrections we're going to make here. It's going to be a bad spin.
It's going to get wild out there. Okay, so this is any notes here. This is extremely significant here. This formula is empirical and it includes the effect of curvature and the atmospheric refraction. What does that mean? It's not observed. It's not a result of observation. It's empirically calculated from how you fit a curve. So they have their
And
30.
it's claiming that there's no such thing as sorry, Alan, but
No,
it
you're
just
good,
bugs
you're
the
good.
shit out of me. It
You're
also
good.
claims that there's no such thing as a variable lapse rate, and that might have also an effect even more profound than this formula. You know what I mean? Quantitatively speaking.
Yeah, this is just to give them what they need to, get to the ball, right? This isn't even like you're saying, this isn't even accounting for anything dynamic. This is like what they need specifically mathematically to turn any height to make it the ball. Extremely significant here. So now we get into atmospheric refraction here. So for every elevation angle, starting from 0, 1, 2, 5, 10, 20, 30, 40, 50, 80, all the way to 90, we have different values here to put in that are derived from not only terrestrial refraction, which is temperature and pressure, which is, normal variable, all good there, no complaints. But then they get into where we're doing this coefficient times the cube of the angle. What are these numbers? Where do they come from? Where do these coefficients come from? How do these refraction corrections, celestial refraction corrections, come out of these angles, you guys think? Well, we'll dive into the how those were derived here in a second, but we're going to look at applications of them, right? So depending on how accurate you need to be, you could apply and depending on the elevation, you apply different formulas. So there's not just like a single one. There's one per elevation. And if that one doesn't work, you can swap in another one. And if that doesn't work, you can swap in another one that has adjustable variables that will allow you to adjust your temperature and pressure so that you can always have the output that you need. Because the coefficient here is gonna like guide you back to the ball, right? As a function of how you're adjusting the temperature and pressure that the table was that this coefficient was derived, or from the table that the coefficient was derived from itself, which is from similar so-called atmospheric conditions, right? All right. So let's see here. That's going to be our third correction now. And remember, we have the, this isn't even where we're seeing it, right? We're saying that it's actually in a different spot now, right? From where we see it. All right, so baseline refraction values of R naught are not measured. They are derived from a fictitious idealized atmosphere with smooth vertical density gradient that assumes a curved Earth. The correction factor F is based off of real world temperature and pressure. It doesn't recalculate physical refraction. It simply rescales the pre-computed values, right? Like all this stuff. We'll get into the integration and expansion series and all that and how it like fits the curve, but that's what that means. Like that's the output of it. It gives you these coefficients when you do that. Real world deviations will never falsify their model because they're scaled into it. Has anyone here ever tried to falsify Earth curvature via terrestrial observation alone, just looking off into the horizon? Anyone? How many people heard? What about refraction? Did you account for refraction?
Flat Earth Math is in the comments right now doing exactly that. As you were talking about it, he was doing it, like reifying his model. He's like, take a depth correction, add it to a nautical sextant, and boom, globe. There it is every time. It's like, yeah, no, we get it.
Your conclusion was my premise. Your
I guess I jumped the gun there a bit.
Your non-empirically derived formula that gets you back to the ball as a function of elevation off of the ball. Yeah, you don't say. All right. And the ball, by the way, right, isn't even the ball. It's the center of like how you perceive the heavens above you. It's the radius of your vision, coincidentally, which happens to be from where you're standing to where you see at the equator in terms of the celestial. So that's weird that they're the same radius. Anyway, moving on. In effect, any observed angle is cohort. Man, I have such a hard time with cohort. Can't do it. Somebody help me out. I'm stuck.
Would you believe coerced?
Coerced.
Plain old coerced. Yeah.
Coerced. Thank you, sir. Coerced into fitting a curvature framework through environmental scaling and pre-modeled spherical functions, not through direct measurement of light paths. Guys, I can't wait to show you how they calculate this. It's awesome. Thus, refraction correction is not a natural phenomenon. It is a model binding operation. That's exactly what it is. The input is the globe. The output could not possibly not be the globe. So here we have Willis John in 1941, the determination of astronomical refraction from physical data. So what they have here is they'll take a snapshot of the sky on one night. They'll take some meteorological data from that. They'll take some measurements of the temperature, pressure, etc. Right, and then they'll model out what the distribution of the atmosphere, like the mass distribution of it is, so that they can calculate different things based off of density, right, for the gradient, because what they're going to do here is use an expansion series to curve fit a log table that they're using, or that starts as a baseline of that snapshot of the conditions on the night. And they're going to go through several different mathematical ways to integrate this into the ball. And what the output ends up being is essentially we have, imagine you're standing at the center of a ball, right? You're like you're at the 0 point of the 39 and 59. And then everywhere at every distance radially outward and every elevation angle radially outward, you have a smooth atmospheric gradient that assumes, no dynamics essentially, right? It's basically a static atmosphere with assumed conditions, so that you have a nice smooth gradient that's layered concentric circles outward from this radius. Now, once you have that, you can take your terrestrial observation and any elevation angle that comes out of this expansion series will have a curve fit to it that will tell you what you need to use as a coefficient to adjust your, like these coefficients here, right? This 34.11 plus 4 or 5, like all these things that come out of this. This is the output of this, of this expansion series. But then once we have this elevation angle, right? Once we're at 10 elevation, okay, well, we use this part of the series and it gives us, these numbers here. We input to the formula relative to our angle. Boom, there we go. We just move the star to where it needs to be even further, right? So this isn't based off of measurement. This is modeled out specifically of multiple layered assumptions of a globe, right? And conforming things in a way that isn't even dynamically derived, right? This is a static model. They assume that there's no radiation disturbances, there's no convection, there's nothing that would create a mirage, no temperature inversions, nothing. All the things that happen regularly, every time we take a measurement and they're like, oh, refraction, temperature inversion, convection, radiation, whatever, right? All these things, they don't do that for celestial refraction. They have a smooth concentric gradient of circles. And so we get left with equation 21 here at the end of all of this. And the secant squared of the zenith gives them, it's not this thing that they're doing here isn't a physical law. It's entirely dependent on how they're assuming the mass distribution of the atmosphere works, because depending on how you integrate that, you can get two different numbers here. So he's showing here 6 arc seconds, right? Stone was talking about, remember the magnitude of these corrections when we get into this, right? So here we're at the output of all this, right? There can be a difference in arc seconds based off of 6 arc seconds based off of how you decide to distribute the mass of the atmosphere, right? These aren't outputs of actual measurements. This is just modeling. And then which output best makes it so that if I reference this star at a 3959 radius, is it going to be at this geographic location at this time? This is all they're doing. It's like it's not even celestial refraction. It's a celestial correction. Okay, so we have this equation broke down here on the side for what all the variables mean. So the refraction angle, Z for the zenith angle of the observed body, and not the refractive index of the observed location, correction factor that you can put in for your temperature and pressure, like I was talking about earlier, local vertical height above Earth's radius, normalizing the refraction gradient with the constant that was output from calculation from the curve fit, which he says is equal to 4.9566. That's all this is. This has nothing to do with the shape of the Earth. This is a model of the atmosphere to use a coordinate system for one hemisphere at a time. Now there's more. If you're going to use the moon or the sun, there's additional parallax corrections that you need to make. So because you're on the surface of the Earth, right, you also need to consider that this whole time you've been building corrections to move the position of a star to compensate for a position of where the observer isn't, right? Which was a huge point of contention for the celestial theodolite, which we'll be covering at the end here. But this is insane. So now the apparent position of the body isn't not only where we, it's not only not where we see it, but actually it's additionally not where we see it, because we have to assume that we can go to the center of the Earth and look up and see what that deviation would be relative to that position. So the difference in angle from center of the ball based on in our original position on the ground gives us the parallax correction to move it where it needs to be so that it can be at that nice 3959 as well. Because while the stars all move in an equidistant web of 3959, 69 miles per degree, the sun and moon have a slightly different relationship. And so anyway, for the baseline here though, right, they have to get it to that 3959 real quick, at least for the purposes of how they're going to use it. So this is how they do that. If you need to reference the sun or the moon. And then there's an additional semi-diameter correction that you can apply by taking measurements of the upper limb and the lower limb. And the difference in that will give you one final correction to change the elevation of this. Because basically, you need the center point of this body to be like, up in elevation or down in elevation relative to whatever wherever you're at, and because the coordinate system is going to tell you that body is supposed to be at a specific spot. So now we're applying everything to move said body to said specific spot where the observer definitely is not. We correct for the geocentric semi-diameter. The semi-diameter is measured by a fictitious observer at the center of the Earth. All right, cool. Measured where the observer isn't. Got it. All right, so we have this over here for the moon correction, which gives us this output here, which is just a ratio of the moon's diameter. Part of this semi-diameter calculation here is the moon's diameter and Earth's radius ratioed against one another to get this coefficient here. So like you might think, okay, well, that at least means that the moon is that far away. No, it's bound to the radius of the Earth, which is the most important part of the coordinate system. The moon could be whatever, right? It doesn't matter. And we'll get into scale and invariance and angular size here in a second. But this is how they're using these ratios, and because they're using one with the other, they're like, oh, it must be this far, this size, this must be what confirms it, et cetera, et cetera. All they've ever started with was just looking at it and saying, oh, that body's half a degree in angular size in the sky. The sun and moon are both half a degree in angular size. That's all anyone has ever. We don't know the radius of it. We don't know the circumference, diameter, nothing, right? But making different assumptions, you can calculate, what the circumference and radius and all that would be, right? For the angular size to be seen at this size based off of its distance away from us, what it would scale down to be. But you have to make some assumptions, primarily using Venus and whatnot. And that's exactly.
Can we actually go back to those two slides? Because I was checking the figures.
Oh, absolutely.
Go back one more, even than that.
This one?
One more. Yeah. You see just to the up left in that figure where it says less than 3/10,000ths of an arc minute.
Oh, yes.
Okay, go forward a slide.
Yep.
That's the quantification right there. And then here we over here where the SD, the semi-diameter of Venus, can increase to 1/2 of an arc minute.
Jeez Louise.
Okay? Just for those keeping score about order of magnitude of correction in terms of a single degree. That's where we're at so far. 6 arc minutes, 3 10,000ths of an arc minute, and half an arc minute for that other particular correction with Venus. Carry on.
Sir. All right. So to get these defined radiuses and everything for these ratios, right? All they've done is make assertions about Venus. It's funny you mentioned Venus there in that one, because Venus was their key to triangulating the distance to the sun. By assuming that the Venus is the same size as Earth, just based off of it being a little dot that fluctuates by up to half an arc minute. So.
And then they called that the astronomical unit, and then they used that to gauge the whole rest of the solar system and then the world. So it's amazing.
Yep. And so what they did here, right? So we have the history of, Copernicus thought it was 3 million. Tycho thought it was 13. Kepler was a 13 lad too. Very original Kepler. Newton was a 28 lad. Second attempt, came up with a 454. Anyway, so we got this fluctuation here. What does this mean? Well, the angular size is the same. So the only variables that could change with this distance would be the size of the sun that produces the angular size that we see. So all these distances also correspond to a different angular size. Every single one of them in their time was correct when they were derived. Nobody could argue differently under the assumptions that they were made, because that's all it was based off of. Just assumptions. It could be whatever you want. Now we're locked into 93 million miles now because of the relationship with Kepler, Newton, moon landing, etc. Right? They've built upon this cosmology to lock us into these distances as the quote unquote physical meaningfulness of these equations. But they no, that nobody knows, guys, and it doesn't even matter how big they are. The scale, because of scale invariance, it's all going to change proportionally. So 53 or a half a degree angular size of the sun would work if the sun was 46 million miles away and 432,000 miles wide. You can have it 3,000 miles away or 3 million miles away, and it would be 28,000 miles wide. Same exact relationship all the way down. Same for the moon. They're the same angular size, thereabouts. Same relationship. You can have it be 6 million miles away, and it would be 56 million miles wide, etc. So on and so forth, right? And then this would also scale the astronomical unit. This would just refactor everything, and it would just be the exact same. It doesn't matter at all. It's a conceptual model. The physical distance output isn't physically meaningful. The only thing that matters is that body will return in the sky.
In the ratio. Ratio is important.
I mean, yeah, that's what gives them their quote unquote physical meaning, but it doesn't. It all scales proportionally, especially if you're doing it off an angular size. All right, so that leads us into astrogeodetic surveying, which is supposed to be the substantiation of Earth curvature in relation to terrestrial measurements. So what they did was they would take horizontal measurements, they would traverse a distance, and then they would take zenith measurements of stars. And then they would transform and compare the difference between the measurements to see if they were in the correct location, right? Based off of their distance traveled from their original calculation. And this whole entire book, right, is about comparing these measurements to the positions of the stars and making the measurements conform to the stars via corrections, whether it be astronomical refraction, lateral refraction, whatever they need to assume or throw out in measurement. They did, and only kept measurements that would comport to aligning with the zenith measurements of the stars that they need for their coordinate system to be accurate. So when they started doing this, right, because in the first book that we read, they were only accounting for the ellipsoid, like basically saying like the Earth's like not a perfect sphere. It's like it's slightly flat a little bit, so it's going to create some deviations in the angles or whatever, right? So what they did in this later study, right after they already had the corrected positions for the ellipsoid, they were like, okay, well, how do we further correct? How do we further move this blob to make it so that it's intersecting with our star? Well, that's where they introduced gravitational potential corrections. and said that there were gravitational anomalies in the area. When they drop their plug bob, it's not going to the center of the ball, right? Like when you, like it normally would, it's slightly off because of some gravitational anomaly. So they take the difference in that, and they've constructed the geoid model, which is a gravitational potential model that intersects with the geoid, or that intersects with the ellipsoid. Sorry, and to maintain level, right? To have your telescope line up with your star properly, you have to be perpendicular to the gravitational potential of the geoid, and not just the surface of the Earth. Surface of the Earth might, if you just use that, you're not gonna, star ain't gonna be where it's supposed to be for you. This is hugely significant because this is just a book of astronomical corrections and assumptions and throwing out data that doesn't fit the measurements. Shane's done multiple presentations on this in particular, breaking this whole thing down. It's an awesome Prezi. Definitely recommend going back and watching it. But the key takeaway here is that no one has measured the ground and concluded Earth curve. That they're always using an external reference, which is I agree with you. You can't just say the Earth measures flat or the Earth measures curve, right? That's empty rhetoric. What does it measure flat or curved with respect to? The only external reference we have is the stars. But if you're not using terrestrial structural intersections, just looking at the position of the star alone, you can't really know for sure if what you're correcting for accurately represents the ground that you're standing on, right? So that's where we get into the celestial theodolite. We have nice model derived from where the observer isn't and will never be, right? The globe model exists as a function of moving the observer from the surface to the center of a fictitious sphere, while we make corrections to where the positions of the bodies would be if we were standing at the center of said fictitious sphere, looking up at a larger fictitious celestial sphere that intersects with our fictitious terrestrial sphere. So this is where we get into using the difference in elevation between an observer at any given distance and a mountain peak to calculate the raw trigonometry of what that mountain peak would have to be based on the difference in elevation and the peak. Oh, I'm sorry, that gives you the angle for that one. So we get an angle off of this, just a relative angle to some structure off in the distance, right? And then we take that, we get into Stellarium or our favorite astronomical software, right? And we go to the peak of that structure and we set the angle of our reticle for that angle, and we'll wait for stars to line up with that intersection point. And we write down the time. And then we go out and observe the stars from the original position that we derived to get that angle. And if we're referencing the quote unquote true position of the star, which is the position that is given to us in the almanac that is derived from, taking these zenith measurements, minusing out the deviation, etc., right? And they're like, okay, this is where the star, quote unquote is. And then you apply these you apply these corrections to the apparent position, and then that's where it quote unquote really, really is, so we can use our coordinate system. But what we're doing is referencing the true position, right? The uncorrected position in the almanac of the star, and that time that angle lines up with the angle that we derived from the distance in elevation of the mountain, or whatever we're using. And if that angle lines up at the same time that star is no longer visible to us, then the geometric implication is that alpha is equal to alpha over here. And if alpha is equal to alpha, then the hypothetical model of the celestial sphere and the, the visible horizon, right, being coplanar, isn't just a hypothetical model, it's geometrically true. It shows that the visual space and the spatial field are not the same. So we'll perceive things lower in the horizon than they actually are. But based off of occlusion timings, we can tell that the physical object included this or intersected with the so-called physical position of this object. And now we can no longer see it. Pretty straightforward. We have about 37 measurements corresponding to this at different elevation angles. And I'm sorry, different elevations, angles, and different distances. And actually, you can adjust the trig function a little bit, and you could compare what the occlusion timing gives you, like what the physical elevation would have to be to produce that. And we can reference that with what the official reported altitude of the peaks are. And we could see that they're always a little higher or lower than what is officially reported. And next to the flat Earth delta alt, we have the distance squared over r squared, or over r, which gives us how much globe drop there would be relative to that horizon. So if we were going to compare two different models here on raw trigonometric functions with no refraction corrections and just go on raw for raw, right? What we would do is we would take our angle, we would subtract 8 inches per mile squared from it, and we would have two different elevation predictions here. So we would have a prediction of, what would it be, like 2,700, no, it's not it, 2,070 feet. And then so the globe would predict that this would be like 2,800 feet. So it would correspond to a different time in which the star would disappear for us. And all these occlusion timings correspond to times that show that the elevation angle relative to us, that our relative elevation angle corresponds to planar geometry rather than a sphere, because the timings in which these are occluded is earlier, right? It's star in the globe model has to get lower in the horizon. It takes longer, but the stars are getting occluded earlier is what this is showing. And then we could take the difference here between what the globe predicts and what was measured, and we find that the globe is off by 250 feet from this measurement that was done at 50 kilometers for I'm sorry, I said I had the observer height and the peak wrong. So the altitude of the peak is 4,200 or 4,300 meters essentially. But you would subtract 200 from that, this was the observer elevation. So anyway, you would do it like that. So you would predict this would be 200 feet lower than what it's reported to be, which will correspond to a different time. No globe times have thus been measured. All right, and another part of this, right? So we have one of the most significant arguments ever put forward for arguing the difference between how to tell the difference between the two models. We're using the intersection of terrestrial objects and the celestial. We're doing raw plane trig, what it would be for the real object if it was this high versus this high. That's all. And it's coming up flat every time. And there's also an additional thing you can do, which happens when the sun is setting. There's shadow sets. So there's two different geometric predictions based off of a model where the sun is going below the horizon versus it just fades out above the horizon. Two different predictions of how shadows will function on the ground. On a flat Earth versus a globe, the sun setting below the geometric horizon would cause the object's casting shadows to cast a shadow higher than the object itself. So in other words, we should see this shadow from these pillars get cast on this wall. They should rise up above the pillars themselves. We should see this window frame in the back climb up this wall and be higher than the window itself. What we shouldn't see is these shadows extend out, climb up the wall, and just kind of chill out here and fade out and never exceed the height of the object casting it, if the Earth is a ball. Right? The window shadow shouldn't stop here, or like we're right around here, and just fade. Right? So this is what the two differences would look like on a globe. It's kind of hard to see here, but the pillars already were casting a shadow that was higher than themselves, and then the shadow of the Earth, due to the curvature, sweeps across the land and exceeds that. But as we're finishing up here, right before that shadow overtakes the one cast by the window, we see that the window is exceeding the height of the window itself. And then on a flat Earth, you would have this scenario where it's just getting dark. It's not very lit out anymore, right? The shadow stops moving right around here. It's actually, it doesn't. So this shadow should be moving at 15 degrees per hour, right? But what happens is that this stops moving at 15 degrees per hour. It starts slowing down, and then it just fades out. It never exceeds the height, which is extremely important because that's a geometric prediction of a flat Earth versus a globe Earth. Because remember, the asserted dynamic cause of the sun and stars disappearing is that the Earth curve is blocking it, right? So we have a video, or we have some images here from Man of Stone, our local resident quality assurance, right from his window in his westward facing door, casting a shadow in the back here. And what we're going to see is that the shadow never exceeds the height of the window casting it. So from this measurement here, from where it starts and where it ended, we don't see, how high the window is. We don't know for sure. So Stone very graciously took some additional measurements and included some, all the necessary information that we would need to decipher whether or not this shadow truly went above the window casting it or not. So here we have a marker here. This red point is the height of the window, and the shadow is supposed to be higher than this window, or this red point here. And what he measures is that it never goes higher than the red point. And what you can do is you can do a little tricky trick, and you can reverse what the angle would be to produce that based off of the sun as it's going into the horizon. And what we find is that 70% of the sun is still casting light on the wall when it's quote unquote setting, but behind Earth curvature. And if any of that were true, then this angle wouldn't look like this. It would be reversed, but it's not. What does that mean, guys? It means that the Earth is measuring flat with respect to the celestial bodies, with respect to the stars, with respect to the sun. The Earth measures flat. The Earth measures globular. Incorrect rhetoric. Very empty. Means nothing. Measures flat with respect to the stars. Means way more. It has our external reference. We can know just how flat or how curved we are or aren't. That is the big takeaway of this, is that if we're going to propose a model to describe the geometry of this place, and it's going to be based off of, it has to partly be based off of positions of the celestial bodies. That's how we know where we're going. There's no such thing as a map that's been derived independently of positions of the stars. How would you know where you're going at sea? Doesn't make any sense. So ignoring that aspect of it is a huge mistake. But in terms of how to, so that we don't accidentally confuse our corrections to use said coordinate system with, the shape of the Earth, we have these intersections that we can use, these references that show that the Earth is planar with respect to the celestial horizon. Any questions, comments, or concerns, lad?
Just on Stone's thing. So essentially, it should be 30% of the sun being visible rather than 70%. Is that what you're saying? If it was the globe, like it kind of should be opposite. That 70 instead of 70% of the sun still being visible.
No, we're saying that it wouldn't fade out like with that much still visible at all. That we would see the ecliptic rising up like the first model that you saw in black and white.
Right.
That we would see the ecliptic of the Earth overtake the image on the wall, and that just never happened. You can always see the complete image of what's on the wall with the same intensity top to bottom for the duration.
Right. And then it just fades out. There's no hard cut shadow.
Right, and you see that with that 117 millimeter measurement there, that the angle is always positive upward towards the door behind yourself in the shot that we're looking at,
Right.
the magnet. So you know that there's an upward angle going towards the sun at the moment that's fading out. They're talking about how much of it is still above the horizon at the moment. We can no longer see it because of the opacity value of air.
Nailed it.
Right.
Nailed it, man. So yeah, if you're, I mean, like, we didn't know all this when we got into this, right? When we first became flat earthers and stuff, like the AE arguing it that way, super easy, great way to conceptualize it. And I don't think that that's not what's happening, right? But we perceive an arc in Antarctic based off of our hemisphere. Clearly, it has nothing to do with the shape of the Earth. We've ruled out curvature with the most with the most substantial way possible, using an external reference. So wherever the curvature exists, it doesn't appear to be in the ground, right? If we going as far as, using a system to navigate that moves the observer where he isn't, corrects the positions of the stars of where they aren't, it's like that doesn't tell us anything about the shape of the ground, dude. Not a single thing.
But it does tell you the shape of my predefined celestially aligned other terrestrial sphere that will match the celestial sphere perfectly. Can I then claim that's the Earth and win?
That's the only way you could do. That's a rhetorical argument, right? We're using the apparent positions of the bodies to build our model, and that is the only way to argue it, is just through
then comparing observations to my model built on the observations to go, behold, my model predicted the observations.
Yeah. So another thing about predictions, right? So we just went through a whole history of the cyclical nature of the sky and how the precession and movements and everything all still line up with the same things that have, guys, if the stars were precessing at a weird way, they would have to adjust the latitude and longitude. They don't. It's the same forever. So what that means is that the models asserting motion and precession that involve the Earth are false. They're conceptual models. That's a teaching tool for astronomers, right? We can use, like, what did I do with my disclaimer pictures? Here we go. It's okay to use this as long as you know what it is. What this isn't, it is not a dynamic God's eye view of the system overall. This is a map of the position of the stars at night and where the sun is going to be for one observer at a particular time. That's all this is. That's all this is. That's all these will ever be. Now, we can look at, what was that? What was the heat map thing of the Earth where it shows a circle for the heat map? You know what I'm talking about? I think it's on Baldwin's. Is that the... You know what I'm talking about, Shane?
About...
So, like, what I'm looking for is it shows the heat
global
map
average temperature zones.
Yes.
Is that what you're thinking of?
Yes, for
I don't think we have a live one on that though.
Well, anyway, what you'll see is that between the tropics, that's where it's the hottest. That's where the GP of the sun is, right? It's doing a circle around us. Yet we perceive an arc in Antarctic based on where we're at. That's what I wanted to point out, right? It's important to know these things and discuss them openly rather than building a whole cosmological framework on apparent positions and then asserting, that this one made a different prediction than the other one. Well, that's not true, right? Both of these models predict the same thing for the distribution of the sun, but we all just thought it was going to be different because of how we were arguing rhetorically and assuming, physicality. Oh, there we go. Thank you, Shane. That's perfect.
We'll get a better one. Here you go. That one.
Oh, that's great. That's the better one. We'll take a quick gander at that. Now you could say this would only be possible on a globe because how could you see it arc in Antarctic? Only possible on a globe would mean that these timings would all be different and they would all correspond to a globe. And I would be doing a presentation on how the Earth was definitively shown to be a globe. These measurements did not go that way, though. So I'm not going to be arguing that. So in terms of why the sun arcs and antarcs relative to your Hemi, I have no idea. I would assume, like, this is just cosmologically speaking, this place was constructed such that you could follow the sun and it will lead you back to the center. Like, it'll lead you back to the equator. And that is constructed in such a way with the arc and antarc that you will never be outside of the sun. Like, you'll never not be the center of creation, essentially, no matter what hemisphere you're in. I think that's the purpose of it. And that's my interpretation of it. Because if it worked the way that we asserted previously, then there would be times when you were outside of that system, and that's not what we would. That doesn't mix that. You can't be the center of creation and then also be outside of the orbit of the sun. So that's my 2 cents on it. Where the curvature comes from, I would say the sky, due to some mechanism. I have no idea, but it clearly isn't the Earth curve. Let's tune into the chat here. See what the boys have been saying.
Well, I must say that I am most pleased to see that my work is not only included, but used as the punchline in this presentation.
Dude, it's so significant.
Totally serendipitous.
Dope experiment, bro.
Dude, not only do we have the stars, we have the sun. They want
Or I
the
should
sun.
say observation. Yeah.
That we do.
If they want the sun back, we'll have to show negative angle here.
They're going to have to do a little work, aren't they?
They're gonna have to do a little something. Instead of looking at Stone's measurements and concluding, I don't even know what do they even say to refute this, Stone? Have they even tried? They obviously haven't done their own measurements, but like, what do they say?
I can actually tell you what the latest refutation was. I have it in an email, and I'm just loading it again right now as we speak.
Fantastic.
And there it is. Tom McKelvey 3609 says, the sun sinking below the horizon will factually cause the light on the wall to, quote, fade out.
The what? What did he say? Sorry, I zoned out. What did
My
that guy
thing
say?
is your thing.
Okay, here it comes again. I'm going to run it by you again because I think this is profound. The sun sinking below the horizon will factually cause the light on the wall to, quote, fade out.
What the ruck? Your position is my position?
Dude,
No, actually, no, he's saying that the sun sinking below the horizon will actually cause what we see on the wall to be what we see on the wall.
Well, it's
my dynamics is your
not
kinematics.
causally.
Yeah, not causally, but it's
all your
it's
observation
Yes.
belong to us.
Yes, it's a variation on your observation is now my observation, which is preposterous.
See, this is not a refutation. This is just counter assertion. That is
Yeah,
what
like,
I'm
of
being
course
offered
that's what
from
it's
the
supposed to
Globe
do.
crowd.
Counter assertion.
That is a definitive example.
Dude, counter assertion. That is such a good, perfect way to
We make it counter baseless assertion.
end this. Guys,
Yeah, it is kind of inferred, I guess, yeah.
how did they determine if it's circular orbits, the Earth moving slightly not as fast as predicted, but also circles, or if it's an ellipse, or if it's a curved linear?
They can only do it with perceived change in angular size, like the quoted half of an arc minute for Venus. That's how they're doing it with the sun and the moon and all the rest of them.
Well, it's just, you can only argue the correctness of either one through baseless assertion. Right? Neither one's more correct than the other. So that guy's trying to refute your measurements that falsify his position by just making a baseless assertion. It's hilarious, dude.
You remember coffee?
He's saying no. I completely disagree with everything we saw with Shadow Reveal's video as well. He's disagreeing that the globe model would show it like A and that the flat model would show it like B. We observed B, but it's actually A, he says. He's disagreeing with that original premise. But he's giving zero substantiation and zero counter evidence.
Sounds like relativity. Look, we would observe exactly what your model would dictate, but actually the dynamic causes my model for reasons.
I think you have it
Whatever we observe
sussed.
must be observed on a globe, according to them.
was a
Well,
great
that's what we
steal
thought it
position.
would be. I'll do
Look-
some back calculations if needed.
All right,
Yeah,
lads.
coffee had the only other refutation, which was like, you guys ever heard of twilight refraction? That's what's causing that.
Oh
yeah,
yeah.
coffee says there's 3 kinds of twilight, and that's going to change everything too, right?
Yep.
You didn't take that into account when you were measuring empirically to the centimeter or whatever.
To the millimeter, my man. Indeed.
Wild. Sorry, go ahead, Alan.
No, you're good. That's it. I was just gonna go ahead and wrap up. Close out for
Good
the
prezi,
night.
bro.
All right, guys.
Cool.
Thanks for tuning in. Thanks for joining us for this prezi. I had a blast learning about this, and I had such a joy to find out that celestial navigation is entirely based on moving the observer where it was not, which is a lot of the early rhetoric that was put forward to try and refute the celestial theodolite. Why are you moving it where the observer isn't? Like, we're just using that as a reference to see where the star is going to be, bro. It has nothing. We're not moving the observer there. It's not what, like, oh man, I feel so good about our position after after looking under the hood of celestial navigation. I've never been happier to be a flat earther, guys.
Excellent presentation. Thank you.
Thank you, Lily. And while you're on the clock, I'm going to need an ad. When you're ready.
Oh yeah. Yeah, Brushtail Coffee, folks. I love sharing my adventures with it. You know, people stop by my place and I serve them coffee. And anyway, so I have a lot of the coffee grounds, and so I use them around the garden because it's very useful for a lot of things in the garden. Anyway, long story short, my sweet neighbor has a chicken, and so we noticed that the worms do really well where the coffee grind, where I put the coffee grinds, the brush tail coffee grinds. And long story short, her chicken laid an egg made of gold, a golden egg, folks. And that sweet neighbor of mine and we both think it has something to do with the brush tail coffee. So, ah, these adventures and miracles with Brushtail never end. So check out Brushtail Coffee, folks. Yep.
Thank you so much for that ad read, Lily. Much appreciated. So you heard it here first, folks. If you drink Brushtail coffee and you own gooses, they will lay golden eggs. Order your Brushtail at brushtail.coffee. Now, let's get into the schedule for the rest of the week here. What we got coming up tomorrow? We got nothing. Thursday will be research and reading night. Friday will be community Twitter space and or a presentation, or this presentation done over at the OmniTalk server. I'm not sure if that's going to be Friday or Saturday. And then on Saturday at 2 p.m. Eastern, I'll be redoing this for the Czech lads. So tune into that if you want to hang out for a bit. Kicking it with the Czechs. And then Sunday, we're on Globebusters season break. Okay. Monday, Tuesday. Shane, what do you got coming up on Tuesday, bro? You got a new prezi or what?
You making it so I have to make one? I think so. It's been like 3 that you had to do. Then, next week we got more to wand on maps, so that'll be fun.
So here's the thing. I can whip out another prezi in between because you got a debate with Mordwand on the following Friday, or that following Friday. So I'll do next Tuesday, and then I'm going to be going on vacation after that, so you'll be in charge the next 2 weeks after that.
Nice.
All right, schedule sorted live, boys. See you guys next